Very good. Thank you very much. So today I'm going to start with, with the main statement that we will prove in these lectures. And then I will develop a tool. And the first thing that it will allow us to do today is to reformulate somehow the main theorem as an inequality that we need to prove. And then the two last lectures will be devoted. In fact, the technique that I will develop today is something that has been used for many, many years in the Ising model. It has like an immense number of applications. So here we will just see one type of application with it, but there are many of them. Okay, so as I said, I'm going to start with a statement. And just to avoid having to go through, so you remember yesterday, I was thinking of a lattice of mesh size A. When I'm actually gonna here today, I'm gonna focus really on a nice lattice, and actually for the end of the lectures as well. A nice lattice of mesh size 1, and just I'm gonna take points or averages on large scales. So I'm gonna define TFL of sigma to be the sum. So I'm not going to renormalize it, and I'm going to define it as being the sum for x in ZD of f of x over L times sigma x. Okay, so again, f is a compactly supported smooth function. So you see this, I mean, you can also just think of it as rescaling the lattice by a factor 1 over L, and you get the formula that we had before. So it's kind of a matching between A and 1 over L. But, and we don't renormalize. This is going to be just simpler in the notation. And the theorem obtained together with Michael Eisenman a few years back is saying the following. So how did I state it again? So you consider the nearest neighbor Ising model. In fact, ferromagnetic, so just means jxy equal 1 if you are neighbors, 0 otherwise. On Z4. Okay. So in 4 dimensions. Then there exists a constant C such that the following holds. So for any, so I'm not going to write it in full generality, but for any function f, compactly supported, smooth, and also I'm going to ask positive for the purpose of this talk, it's going to be simpler. For any function like that, there exists a constant. In fact, it's an explicit constant. It's just expressed in terms of the norm of f and on the support of f, the size of the support. But let me just write something like that. Such that you have the following. For every z, when I look at the characteristic function of TFL, okay, and I look at the Ising model at beta c, well, when I compare it to what I would get if it was a normal random variable, which would be e to the minus z squared over 2 times the variance. Okay, so if I do this ratio and I subtract 1, so I'm trying to see how small this is, then I obtain something which is bounded by constant z to the 4. But the important thing is that I get log L to the power c. So it's small, and it's polynomially small. C is actually tiny. So, and even in reality, C is smaller than 1. So when I say polynomially small in log, it's rather algebraically small. Okay, so that is exactly measuring kind of quantitatively how close this quantity is to a normal random variable. Okay. Okay, so sorry. I mean, this doesn't work like that. So here, if I don't renormalize, there's going to be a problem. Sorry. So here, I'm going to renormalize. Sorry. That starts poorly. So I'm going to renormalize by 1 over square root of what I will call sigma L. And sigma L is just sum for x and y in the box of size L of sigma x, sigma y, beta c. Okay. Why do I do that? Because you see here, so maybe that's, well, I mean, I'm going to make a bunch of remarks. So let's mention a few remarks. The first remark is that T indicator function of 0, 1 to the D, L. So if I look at the variance of this quantity, what do I get? Well, this is exactly made in such a way that this is a variance of the non-normalized function when you take f equal indicator function of 0, of -1, 1 to the D. So this thing has variance 1. So the renormalization is exactly made in such a way. So of course, it's not a smooth function, but that's not so important. So it's just made in such a way that typically these people have a variance of order 1. Okay. And then we are comparing characteristic functions. So this is roughly saying, so that's the first point. The second point is that this is, I mean, this is saying that TFL of sigma is roughly a normal random variable with the right variance. So that's for the first remark. The second remark, I mean, the third remark, sorry, is that you can extend this a little bit. Here I want this to be at beta c. I stated the result at beta c. In fact, the result extends. To any beta smaller or equal to beta c, as long as you assume that the L you take here, where is L? Here. This is also for every L. The L that you take here is smaller than what we call the correlation length. I don't want to be entering into detail to what is the correlation length. Just in words, it's the inverse of the rate of decay of correlations in subcritical. When you are at beta smaller than beta c, in fact, correlation decay exponentially fast, and the correlation length is 1 over this speed of decay. So you don't want L to be too big for a simple reason. Physically, the correlation length is the first size at which you start to really see you are subcritical. Below it, you look fairly critical, things decay algebraically. Above it, they decay exponentially. So as long as you are in this regime, it's fine. Why do I mention that? Because for people who think about the first interpretation in terms of Euclidean field theory, if you are trying to build a limiting object, you can indeed fix beta equal beta c and take the limit when size goes to infinity. You will end up, that's a prediction, you will end up, in fact, with a Gaussian free field. So here we are proving it's a Gaussian process that you obtain in the end. In fact, it's a Gaussian free field. But you may want to be getting other type of Gaussian processes. In particular, you may want to be obtaining massive Gaussian free fields. And that you can obtain by taking double limits when beta tends to beta C, L tends to infinity with L of the order of the correlation length. So it makes sense to actually extend the result to this regime. There is one thing that is a little bit annoying, and that's also why I wanted to mention this third comment, is that as for today, we only know how to do it when beta is small or equal to beta C, which is not something so natural. You may want to be taking the limit when beta tends to beta C, but by values that are larger than beta. This we don't know how to do. This is an interesting open problem. In fact, you may be taking L larger than C of beta when beta is smaller than beta C. It will give you a white noise, so you will not get something interesting. And this is trivial to obtain, essentially. Okay, so another comment that yesterday I mentioned this Hamiltonian, where I was having like sum of jxy, let's say phi x, phi y, and then I was having another terms which was looking like that, and then the phi x was in R, right? What I call the phi 4 lattice model. So those are phi 4 lattice model. And I told you, well, if lambda equals 0, you get something Gaussian because you have just a massive Gaussian free field. If you take the right limit when lambda tends to infinity and b tends to minus infinity, you get the Ising model. So these models are an interpolation between the two. And it doesn't come as a surprise that if you manage to prove this somehow for the most correlated system, the system for which this second part is the worst, then in fact you manage to do it for every phi 4 lattice model. So the result extends to all phi 4 lattice models. I will not be doing it in these lectures. I will focus on this interesting case, but I wanted you to know this. Okay, and in particular, that means that any convergent subsequential limit of these models is Gaussian. So you really don't manage to create anything else than Gaussian processes. And the last comment I want to be making, two last comments. So when D is strictly larger than 4, then this was known already, that I mentioned on Monday, but so then it was known from 1982, and these are two papers, one by Eisenman and one by Fröhlich. In some sense, so Michael Eisenman proved the result using what I will use later, which is this random current representation. Jörg Fröhlich used it using the Bridges, Fröhlich, Spencer walks. Nowadays, we understand that these were related techniques, but at the time, it was really two independent papers. And one thing that is important is that they get the result, but with with log L to the C replaced by L to the D minus 4. So you get a polynomial rate of decay here. Okay. That was one before last comment. And the last comment is that for D equal 4, these things were known in one context, is if you take the phi 4 lattice models but you take lambda very small. So phi 4 lattice model with lambda tiny. So in some sense, you feel you are starting close to a Gaussian process. Where then in this context, you can actually run a rigorous renormalization argument to prove that you converge to Gaussian Fifi. This was first done by Gawecki, Kupiainen. It's putting too many P's. And I don't have the date, but it's also in the 80s. And then it was redone by Bridges, Bauer-Schmidt, Slade. There is also Hara, Takashi. I mean, there are a bunch of ways now to derive this, but here's the important argument. I mean, the important thing I want to mention is that this is using renormalization argument, and in some sense, so here you have Ising, here you have GFF. So it's really when you start, and this is a line of phi 4 lattice model, it's really when you start close to the end, right? I mean, actually, I mean, today renormalization techniques are always perturbative in nature. So it doesn't really exclude on its own. It's not a very good argument to argue that you never managed to get something non-Gaussian, because you are just focusing on one area of the space of models, which is by definition kind of close to the fixed point, to the Gaussian fixed point. And it doesn't exclude the fact that somewhere else in space you would have another fixed point. Okay? If you do it for this whole line, it starts to be looking much more convincing. And okay, and because it's perturbative in nature, I mean, we don't use at all the same approach. The downside is that they actually get the full limit. It's not just that they get something Gaussian. They get that it's Gaussian free field. We cannot do that for now. At the end of the lectures, if I have time, I will mention a recent approach that we are developing where we hope to be getting it, but for now we don't have it. Okay, so that was for the statement. So now, let me give you a crash course on the technique that we are going to use, which is called the random current representation. So I'm going to take a little bit of time for two reasons. First, because we are really going to base most of our analysis on this object. And the second is that it's really very useful for many reasons. As I mentioned on Monday, the continuity of the phase transition is relying on this technique. And for instance, if you want to prove that you have exponential decay of correlations for the Ising model, when beta is strictly below beta C, you also use this technique. It's really practically every single result on the Ising model has some nice parts that uses this. Or if it doesn't, it's just that people didn't know about it. But once you know about it, you can redo things with this technique. So it's a very, very powerful technique, not due to me. It was introduced by Griffiths a long time ago, and it was magnified, let's say, and put to another level by Eisenman in his 82 paper. So definition. So a current N, this will just be a current is just going to be a function from the edges of a graph. So I'm going to fix G, a graph with vertex set V and edge set E. So a current is just an element N, which I would write NXY for XY an edge, an element of the function from edges to the integers. Okay, so at every edge, on every edge of my graph, I just put an integer. Okay. So current, there will be a natural thing that we want to associate to currents is a source. A source is a vertex x in V, such that delta n of x, or delta x of n, which by definition is the sum of a y neighboring x of nxy, if this thing is odd. Okay? So the sources are the point for which the sum of the current for edges that are incident to this point is odd. Okay? So if I would give you a smaller, I'm sorry if I'm going too slow, but I want to be sure you get these notions. So here, this point, for instance, the delta x of n is 7. So this is a source. Here we get 6, 4. Oh, I managed to get only. Yeah, thank you. So these 2 points are the sources. Yeah? Every other vertex has an even number of when I sum the currents. And the set of sources, I'm going to give it a name. It's going to be useful. I'm going to denote it delta n. Okay. And last thing I want is I want to define the weight of a current. So this is going to depend on the parameter beta, and it's going to be the product for every edge of beta to the nxy over nxy factorial. Okay, so these are definitions. There is nothing, I mean, it's just a terminology. We call current things like that. And now what do we do with it? So the first thing, so I mean, I'm going to focus always on nearest neighbor edges. That's why, I mean, nearest neighbor ferromagnetic models. That's why I take currents to be defined on edges. In general, you may be taking currents defined on any pair of points. It's just that the definition you will cook up would exactly make it that if there is if jxy is 0, then the current will always be 0 between x and y, like on the edge between x and y. So you restrict yourself like that. If you take nearest neighbor ferromagnetic, you are certain that only nearest neighbor edges have a positive current. That's why I restrict it like that. Okay, so let me mention a few properties of these currents. So the first one, and this is a simple exercise. So proposition, fix a subset of the vertices. Okay. Then, if I look at what I will call Z, G, A, beta, which I'm going to define as just a sum for all sigmas of product, of sigma A exponential of minus beta H sigma. So sigma A here is just a convenient notation. We are going to use it a lot for the product of the spins on the set A. Okay, just a convenient way of denoting that. So Z, G, A, beta is just, if you want, the unnormalized average against sigma A. So this, I claim that this is equal to 2 to the number of vertices times the sum on currents that have exactly sources A of W beta of n. So I can rewrite these partial sums, this weighted sums, sorry, in terms of sum of currents, just currents having a certain constraint on the set of sources. sorry. Okay, so how do you get that? I mean, for people who already saw this type of I mean, it's not very surprising, this type of rewriting of a certain sum against an Hamiltonian, rewriting in terms of combinatorial sum over a certain object having some constraints. This is something you see very often, and in particular, that's what you get in high temperature expansion of the Ising model or of other models. And how do you get this type of things? Well, usually what you do is you just expand. You do an expansion of your Hamiltonian. So here I'm not going to do it because I can really promise you that anybody in this room can do it on his own. But basically what you do is that you write the product of the e to the beta sigma x sigma y, where x is neighboring y. So this is just e to the minus beta Hamiltonian. You just expand this as sum for nxy equals 0 to infinity of beta nxy, I mean, beta sigma x sigma y to the nxy divided by nxy factorial. So you just Taylor expand each one of the terms. You invert the sums. And what will end up at the end is that you are going to have a certain sum over configuration sigma, and this sum is going to be either 0 or 2 to the number of vertices, depending on the powers that you get in. Just do it on your own if you are interested. It's really similar to what you do for high temperature expansion. For high temperature expansion, what do? You write this as cosh of beta sigma x sigma y plus sigma x sigma y and sinh of beta sigma x sigma y, and you do the expansion again. You exchange the sum and the product. Here you do the same, except it's with Taylor expansion. So at this stage, it's not so clear why these random currents would be better than the high temperature expansion, especially that the high temperature expansion is something that you can get in many models. So why on earth would this be better? Well, we will see it in a second. Just a remark, an application of, I mean, that's a corollary of the proposition there, is that if I look at the correlation itself on G at parameter beta, well, the correlation itself is just the ratio of ZGA beta with the partition function, and the partition function is nothing else than ZG empty set beta, right? If I put A to be empty set, I just get the partition function. So what do I get from that? I get that the spin-spin correlation, I mean spin-spin-spin-spin correlation if you have a bigger A, is just a ratio of weighted sums. The numerator is summing over current with sources A, and the denominator with current with sources empty set. So sourceless currents. And this is just taking the ratio, like applying the proposition here twice for the numerator and the denominator. Okay? It's very similar to what you get for high temperature expansion. You exactly get the same. Once you have the expression for the weighted sum, then you just take the ratio and you get the spin-spin correlations. And that's why it appeared in the very early on. It's when people were trying to get correlation inequalities for spin-spin correlation, they naturally introduce these random currents. Okay, so what makes random current in some sense more powerful than just standard expansion like the high temperature expansion? And here I know usually you should be careful in science not to be overstepping, but here I do think that random current allow you to do many more things than high temperature expansion. It's just that there is a cost. It's just that random current are not that powerful for many models. It's very powerful for Ising. It's just not so efficient for other models As for now, we don't know. So there is going to be a tool that is specific to Ising and to model in the Ising class. It's not true for people who know about the XY model or the spin-ON model in general. It doesn't extend to other N. So it's specific to Ising and 5.4 and things like that. But it really gives you a lot. So this is going to be what we are going to do now. So there is something about currents when you duplicate them. So it's very nice to take two currents. And this is reminiscent of something in the Ising model, which is that it's very nice to be taking pairs of Ising models. People realize very early that having two Ising models coupled in an independent way is actually very useful. And we are going to see that immediately. So let's make a definition. So I'm going to define, so for a current, I'm going to define an element n hat, which will be a function from the edges into 0, 1. And this n hat of xy is just 1 if nxy is strictly positive and 0 otherwise. So it's just saying the current is positive or not. Okay. Once we have this, we can state, maybe I'm going to state it here. We can state our main combinatorial tool. It's called the switching lemma. And the switching lemma is saying the following. I'm not going to write the most general version of it, or do I? Well, since I'm not going to prove it, maybe I should be writing the most general version. So consider a subgraph h of g, but otherwise just think h equal g. That's fine. And a function that is taking currents on the edges of G, I mean currents on G, and say it gives you something real. Okay? It's a function from currents to R. So the switching lemma is saying the following. Imagine I take the sum and I take one current on G. And one current on H. So let me call them N1 and N2. And I'm looking at a function of the sum of the two. Okay? But imagine that I'm telling you the first current has sources A and the second has sources B. So I'm going to ask that the first current has sources A and the second current sources B. Okay, so I'm summing on currents with a prescribed source. Okay, so the sum of the two currents, if you have one which has sources A, the second has sources B, the sum of the two currents, you will agree, has sources, a symmetric difference between A and B. Okay. So I could be tempted to try to move one of the sources, source set, to the other guy. Maybe I would be more interested in having that the second current has no sources and the first one has all the sources, meaning A, symmetric difference B. So how does this compare, if it does, to this quantity, where I take N1 still edges of G, N2 still a current on H, but I'm asking that N1 has sources empty set, and N2, sorry, and N1 has sources A, symmetric difference B. Okay, so I move the sources from A to B, and I'm looking exactly at the same functional. So there is a way, and that's what the switching lemma tells you, there is a way to give an equality here, to put an equality. So to be able to switch the current, the sources from second current to first current. The only thing is that here, you need to add something. You need to have the indicator function that, I don't know why I put the trace before, sorry. The indicator function that n1 plus n2 belongs to the event what we call FB, and it's actually n1 plus n2 restricted to H, belongs to FB, where FB is the following event. I mean, the following set, because there is no real probability measure here, where FB is a set of K, so that there exists K prime, or the set of M, so that there is K smaller than M with a set of sources of K equal B. So what does it mean? It means here I'm allowed to switch the sources if I know that in n1 plus n2 there is a subset that that has sources B. Okay. So of course here you notice this is automatic, like n1 plus n2 always have a subset which has sources B, simply because there is n2. Right? N2 is exactly a graph current on H which has sources B, set of sources B. Here it's not automatic at all. So I'm adding this constraint. As soon as I add this constraint, I have an equality. Okay. So this lemma is not complicated to prove. Hence, I'm not going to prove it. No, it's not that simple, but it's not very long. It's just there is a nice combinatorial observation that you can make, and once you have it, it's a few lines. But it's really not a few lines you want to write on a board, except if forced to. Okay, but just to realize, I'm going to give you a few applications of this thing. I mean, I think the first time you see this, it doesn't really help so much. Yes? Any A and B. You can choose whatever A and B. Yeah. That's a good point. Yeah. Yeah, I mean, otherwise it would just be empty. Like both things would be empty. So you can take any A and B, just that you are gonna. It's a little bit like if you take A to be odd, cardinality, then this thing is vacuous because there is no current with other set of sources. So indeed, it only makes sense when A and B, when B is included in H. But a priori, you don't have to force it. The formula is true nonetheless. Okay. So let me give you a few applications of that. Trust me, it's not that I'm hiding 30 pages like proof. I mean, it's a few lines proof. And same thing for the other one. So now let me prove to you a few inequalities that you probably heard about. Sorry? Indicator of n1 plus n2 belong to FB. It's just here when you take H subset of G, you want to restrict the current to H. But otherwise, sincerely, if you are, I mean, you are going to see why I mentioned the H included in G. Otherwise, you can just remove this and just think that all your currents are in G. It's perfectly fine. It's a sub case. And it's already, for instance, for the first application, it would be perfectly fine. So applications. So this is not directly related to what we are going to do, but I think it's so nice that I don't resist. So there is, for instance, you could try to look at the product of, let me write it here that it's that I have the whole. Imagine I look at this quantity. I'm not putting G beta, but I mean, I'm just saying I take a graph G, I take a beta temperature, and I look at the product of spin-spin correlations. So you agree that this is like ZA, ZB over Z empty set, right? If I drop the G and beta notation. So this, if I write it in terms of currents, what does it give me? Here I have a sum. The first guy is a sum over N1 equal A of W beta and W of N1. And the second is a sum over, so this is going to give you this. And this one is going to give you a second sum, which I can write in the same place, this time with sources B of W and 2, right? This is the numerator, up to a 4 to the number of edges, which is going to disappear because I have this here. And on the bottom, it's the same double sum, except that the sources are empty set. Right? Okay, let's apply the switching lemma to the top. I realize that, do you see well? I'm sorry. This is a little bit, so let's apply the switching lemma. When I apply the switching lemma, notice that this here, I can put B on A, right? So I'm going to have the sum for N1 equal A symmetric difference with B, N2 empty set, WN1, WN2, and then I have this weird indicator function. And on the bottom, I have the sum N1 equal empty set, N2 equal empty set. Right? But when I write this, you agree that if I'm only interested in an inequality, I can just write the inequality by dropping this term. Right? And when I did that, after I do that, what do I get? Both on top and bottom, the second current has sourceless 0. I mean, empty set, so I can remove it. Just the ratio is equal to 1. So this is nothing else than sum for N1 equal, I mean, on currents with sources asymmetric different B, divided by sum over currents with no sources. This is just sigma A symmetric difference B, which is, by the way, sigma A, sigma B. So what did I just prove? I proved Griffith's second inequality. The product of spin-spin correlation is smaller than the correlation of the product. And by the way, I even have some kind of grasp at what is the difference between the two. If I write the difference, it's going to be something related to the indicator function that I don't have a connection with. Okay? So that's one application, for instance. You get Griffith's inequality very easily. Second application that I want to mention is that if I take exactly the same quantity, but I just take B equal A. So I get sigma A squared. And here, when I didn't do the inequality, I get sum over N1 with no sources and N2 with no sources, right? So I actually get exactly probability. I'm going to explain this notation that N1 plus N2 is in FA, where this is what? T empty set is the probability measure on sourceless currents, which give probability proportional to the weight to each current. Right? If here I have sourceless as well, then I'm just looking at two independent currents, sample according to this probability measure, and I'm looking whether the sum satisfies FA. So I can rewrite the spin-spin correlation squared as the probability of a certain event. So probability measure on sourceless currents, attributing probability proportional to the weight of currents. So I rewrote this, the spin-spin correlation squared, as a probability of something. In particular, note that if A is just xy, two currents, I mean two sources, then it tells me that sigma x, sigma y squared, so the square of the spin-spin correlation, is the probability empty set. So I sample a first current with empty set. I sample an independent current with empty set. And I look at N1 plus N2 belongs to fxy. So what does it mean N1 plus N2 belongs to fxy? That means that N1 plus N2 is such that there exists a subcurrent that has sources x and y. This, if you think about it, it's exactly meaning there is a path between x and y in the trace. There is a path of positive current. So here you end up, this is nothing else than saying, if I look at the percolation model given by N1 plus N2 hat, there is a path from x to y. So I rewrote the spin-spin correlation question as a percolation question for a very dependent percolation model, which is obtained by sampling two independent currents with no sources. Each one is sampled, the probability is proportional to the weight. And then I sum them and I look at when they are positive. If they are positive, I say the edge is open. If they are both zero, then we say the edge is not open. And I look at whether there is a path between x and y. Okay, so that is to maybe conclude. I mean, if you think back about the talk of Monday, where I mentioned that we rephrase spin-spin correlations as a percolation model, this is a typical example. Let me just, I have 1 minute. I'm not going to do anything more. Just, I'm going to give you 2 exercises for tomorrow. It's not even like, it's just something that you can think of. Is prove, so 2 other applications prove that sigma A in the graph H is smaller or equal to sigma A in the graph G. And again, this you can get very easily by a switching, this time using H included in G. That's why. So this is the monotonicity in the graph, or in coupling constant, if you prefer. You can always think that when you increase the coupling constant, you are just increasing the graph. So this is the monotonicity in this. In particular, it gives you immediately monotonicity in beta. And let me give you another application, a little bit cooler to get. So this may require a little bit more thought. But it's called the Simon-Lib inequality, and it says the following. Imagine I take a set S, which contains 0, and X that is not in S. The Simon-Lib inequality gives you what you would get for random walk, which is that the spin-spin correlation between sigma 0 and sigma x is smaller than the sum for y on the boundary of S of sigma 0, sigma y, sigma x. So if you have your set, you have a set S like that, and you you have X outside, it's kind of saying that you can get the correlation by summing over the Y's. So this is called the Simon inequality. The Simon-Leib inequality is the same thing where here you look at the graph restricted, I mean, the spin correlation here is restricted to S. Try to get this inequality using the switching lemma. I will start with that tomorrow. It's very cool. And you see, I mean, all these inequalities are the fundamental inequalities in Ising. Like they are used all the time. And you get them by like trivial application of the switching lemma every second. I stop here. Thank you very much.